Hi class, welcome back. Today is 12:4 multiplying polynomials. Main ideas for today's lesson will be finding the probability of two independent events and finding the probability of two dependent events. So let's start off with the probability of two independent events. An independent event, remember, is when one event, the second one, does not matter what the outcome of the first event is. So for instance, flipping a coin, if I flip a coin once and get heads, that has no bearing on what the second outcome is. A dependent event is when the second outcome is affected by the outcome of the first. So for instance, if I have marbles in a bag, if I choose one of those marbles and I do not replace it, now that probability is affected because there's one less marble in the bag. So that's the difference between an independent and a dependent event. So to find the probability of an independent event, we have two events A and B which are independent, and we want to find the probability of these events. Well, the probability of A and B occurring, meaning both of them, is simply the probability of A times the probability of B. Now, this formula can be applied to any number of independent events, which means if I have 5 independent events and I want to figure out the probability of all 5 occurring, it's simply the probability of each one multiplied together. So let's give a couple a try here. First example, Gerardo has 9 dimes and 7 pennies in his pocket. He randomly selects one coin, looks at it, and replaces it. He then randomly selects another coin. What is the probability that both of those coins are dimes? So the key word here is that he replaces it. By replacing this first coin, the odds are not going to change between the two events. This is what makes them independent. So to start off, let's look at the two options. So here's option 1, here's option 2. The first coin he picks out, he wants it to be a dime. Now he has a total of 9 dimes and 7 pennies for a total of 16 total coins in his pocket. Probability is the number of successes over the number of outcomes. 9 dimes, 7 pennies. There's 16 total coins in his pocket. Chance of success, 9. So 9 out of 16 for the first one. Now, once he picks that dime, he then puts it back in his pocket, leaving 16 coins in his pocket and still a chance of 9 possible successes. So this would be coin 1, this would be coin 2. To find the probability of both times this being a dime, 9/16 times 9/16, which gives me an answer of 81 over 256. And as always, we can represent that probability as a decimal, 0.3164, or as a percentage. So almost 32% chance of him picking back-to-back dimes. Alright, second option. Gerardo now has 9 dimes and 7 pennies, so same situation before. He randomly selects one coin, looks at it, replaces it. He randomly selects another coin. What's the probability that both of his coins are now pennies? So we just did the dime example, now let's do pennies. So again, 16 coins in his pocket, 7 of them are pennies. That's coin number 1. He puts the coin back, which means there's still 16 coins in his pocket. 7 of them still pennies. Multiply them together, we get 49 over 256. Probability can be expressed as a decimal, 49 over 256, which is 0.1914, or as a percentage, which is 19%. So a much better chance to pick a dime twice in a row than picking a penny twice in a row, which makes sense considering he has more dimes than pennies. So let's expand on the number of events we have. This time let's suppose we have 3 dice that are rolled. I want to know what's the probability that 2 dice show a 5 and the third shows an even number. All 3 of these dice are being rolled individually, so they're all independent of each other. So because they're independent, I can just simply figure out the probability of each one happening. So the first one, I want a 5. Well, there's 1 5 out of 6 possible numbers on a dice. So that's dice number 1. Second dice, I also want a 5. There is 1 5 out of a possible 6 numbers. The third dice I now want an even number. So again, there's 6 numbers on a dice. An even number could be 2, 4, or 6, which means there are 3 even numbers. Multiply them all together, gives me 3 over 6 cubed. Let's see what we got here. 216. And again, that probability can be expressed as a decimal. 0.013889 as a percentage. A little over 1.3%. And 3 over 216 can actually be reduced to 1 over 72. So the probability for rolling 2 5s and then an even number are 1 out of 72, or 1.3%. All right, let's try another one. Let's take those same 3 dice, let's roll them again. This time I want 1 dice to be a multiple of 3, 1 to show an even number, and 1 to show a 5. So let's start with the multiple of 3. Well, first off, this is definitely independent because, again, all 3 dice are being rolled at once. There's 6 numbers on a dice. In order for it to be a multiple of 3, that means it has to be a 3 or a 6, which means I have 2 out of 6. 1 dice show an even number, so 6 numbers could be 2, 4, or 6, so 3 out of 6 for that one. And 1 dice to show a 5. 6 options, there's only 1 5. Now, last problem, we just multiplied them together. I actually like to reduce before I do the multiplication, especially if I don't have a calculator. So 2 out of 6 we're going to call 1/3. 3 out of 6 we're going to call 1/2. And times 1 out of 6. So now when I multiply these together, I simply get 1 on the top. 6 times 6, 36 on the bottom. 1 out of 36. 1 out of 36 is 0.02777, or as a percentage, about 2.7% chance of this happening. It's not very likely that we're going to get a multiple of 3, an even number, and a 5 on a single roll of the dice. Okay, for the second half of this, we're going to take a look at dependent events. Remember, the dependent event is where the second outcome is adjusted based on the first. The second outcome is affected by whatever happens that first time through. So let's say we have 2 events occurring, A and B, which are dependent, and the probability of both events occurring are, again, the probability of A times the probability of B following A. So again, you have to subtract out that one that has been removed and not replaced. And just like before with independent events, this can be done with any number of dependent events. So here we go. The host of a game show draws chips from a bag to determine the prizes for which contestants will play. Of the 20 chips in the bag, 11 show a computer, 8 show a trip, and 1 shows a truck. If the host draws a chip at random and does not replace them, find the probability of drawing a truck, then a computer. So the keywords here are does not replace. This means the second outcome is affected by what happens the first time through. So let's see the situation here. We're going to draw 2 chips. Chip number 1, we want it to be a computer. I know there are 20 total chips in the computer, and of those 20 chips, 11 of them are a computer. So the probability of first picking out a computer is 11 out of 20. Now, that chip is not replaced. So what happens is there's now 19 chips left in the bag. I then want to choose that by picking a truck. So the second chip should be a truck. There's 1 chip that's a truck. There's 19 left. So I multiply these together, which gives me an answer of 11 out of 380. 11 out of 380 as a decimal and as a percent. So almost 3% chance of this game show host drawing a computer and then a truck. Okay, let's try this again, this time with cards. Standard deck of cards. There's 52 cards in the deck. There are 4 suits: hearts, diamonds, clubs, spades. 13 cards in each suit. Let's suppose 3 cards are drawn from a standard deck without replacement. There's your keywords again, without replacement. Without replacement means the cards are not put back in the deck, so they're left out after they're picked. I want to know what's the probability of drawing a heart, another heart, and then a spade in that order. So I'm drawing 3 times. So here we go. First time I draw, there's 52 cards sitting in the deck. I want to know probability of getting a heart. Each suit has 13 cards in it, so that would mean 13 out of 52 for drawing a heart. Times, that card's now left out, and because it's left out, I'm now down to 51 different options. I picked a heart the first time, I left that heart out, so the chances of drawing another heart are now down to 12 out of 51. Again, that card's left out, which means there's now just 50 cards in the deck. Out of those 50 cards, I now want to choose a spade. I have not touched the spades yet, which means there's 13 spades still in that deck. And if I multiply all of these together, we will end up with 13 over 52 times 12 over 51 times 13 over 50, which gives me 0.015, or as percentage, 1.529. Let's get that as a fraction. Fraction. 13 over 850. So if I have a deck of cards in front of me and I say draw a heart, and a spade, the probability that's going to happen is 13 out of 850, or 1.5%. So not very likely that event's going to occur. Alright, let's try another one. 3 cards are drawn from a standard deck of cards without replacement. Again, keywords, without replacement. Find the probability of drawing a diamond, another diamond, and another diamond. So I want diamond, 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 3 in a row. So I start off, 52 cards in the deck, 13 diamonds in the deck. I pick one of them, I leave it out. That now puts me down to 51 cards in the deck, 12 diamonds. I pick that card out, I leave it out. There's now 50 cards in the deck, and 11 of which are diamonds. We'll multiply all those together. So we have 13 out of 52. 13 out of 52, which by the way reduces to 1/4. If you're trying to simplify things a little bit better for you. 12 out of 51. 11 out of 50. Gives me an answer of 0.0129. As a fraction, 11 out of 850. And as a decimal, there we go, 1.29. So the probability of throwing 3 diamonds in a row, and this goes for any suit by the way, you'd see this to be exactly the same, was 11 out of 850, or 1.29%. That's it for our multiplying probabilities of independent, dependent events. I have 3 problems here for you to give a try. As always, the answers are over here in red, so give them a try. Jot down any questions that you may have had from this lesson, rewatch it, bring your questions into class tomorrow, and we'll give some of these problems a try. Have a good night.